Well, first of all, David Neal said that you are awesome. And why is that? Because everything is awesome. So, welcome to an introduction to machine learning using Lego. And in the next hour, we will go through some very basic machine learning theory and see how we can apply that to make a Lego car steer by itself. But before that, a bit about me. Who am I? My name is Jeppe, and I work here in Oslo as a consultant at Itera. And even though I live and work here in Oslo, I am actually from Denmark. And you may know that Denmark is the world capital of Lego. So even from a very young age, I was building Lego. At Christmas, I just wanted Lego, nothing else. And every time I have visitors, I just play with the Lego. And every time that Lego makes a new Lego Technic set, I go out, buy it, and I build it. But I guess you are not here just to see old photos of me building Lego. But I guess most of you have been playing with Lego at some point, and I guess that many of you have also been working with Lego Mindstorms. So let's go back to 1998. In 1998, the first Lego Mindstorms was released. This one, it's called Lego Mindstorms RCX. And I see that some of you are old enough to have been playing with this, but I most certainly am old enough. So when this was released, I spent all my money on this set. So this is actually my first Lego Mindstorm set. And as you probably also know, Lego lasts forever. But one thing that doesn't last forever, that's Windows XP. And unfortunately, you need Windows XP to program this old RCX robot. So later in this talk, I will use a newer revision of Lego Mindstorms. The main objective for today is to make a Lego car steer by itself. And I guess if you have been playing with the Lego Mindstorms, you probably already have made a car which could steer by itself. You probably made a car that looked a bit like this. It had tracks and a light sensor. Then you can use a fairly simple algorithm that says when the light sensor sees black, then drive left. If not, then drive right. And we see here that it is actually working. It in a bit of a wiggly motion, but again, it's working. But this is not a real car. As cool as it would be to have tracks on our cars at home, that's not really the case. A real car has wheels and have a more normal steering. So let's try and build another robot that looks more like a car. A Lego car which has wheels and a more normal steering. Can we change the algorithm just a bit and still follow a black line? Well, if we start on the right side of the black tape here, and then start driving, then we steer left, wait for a bit, steer right, wait for a bit, steer left, and so on. It is possible to follow the line, but the motion is even more wiggly than the one we saw before. So this might be a bit too simple if we want a Lego car to steer by itself. Yeah, but then on the right, someone said Tesla, and that's right, this is a promotion video from Tesla. And Tesla, when it comes to driving, they can do almost anything. They can follow the road, they can keep a certain distance to the car in front of it, they can take turns, a Tesla can also park itself. And this might be a bit too advanced, what we can do in just 1 hour. So let's do something in between these two problems. So let us define the problem we want to solve as we want a Lego car with normal steering, which can follow a black line. We want to use machine learning and see what is the most simple machine learning algorithm that we can use and still solve this problem. So let's skip Lego for a bit and just focus on machine learning. We will now go through some very basic machine learning. And this is an introduction, and we do not have a lot of time. So again, it's just the very basic theory that we will look at. Machine learning can solve many different problems, and there are many different algorithms. But throughout this talk, I will just be talking about supervised learning. And here we have a definition of supervised learning, and let me just read it. Supervised learning is the machine learning task of learning a function that maps an input to an output based on example input-output pairs. Maybe this makes sense to you, maybe it doesn't. So let's look at an example. For example, if we want a machine learning model which can map an image of an animal to what kind of animal it is, then we just saw that we need some input-output pairs. We can also say that we need some features and we need some labels. And here we have, let's see if this is working, we have an input, that's the image of the tiger, and we have the wanted output, what we want the model to predict. That's the tiger here. And we need a lot of sample data. So let's collect a lot of sample data and put it into a magic algorithm. A lot of data. Then this algorithm, it calculates for a while, and out comes our trained machine learning model. And let's see what we can use this model for. We can use this model to, if we give it an input, in this case, an input of a cat. Apparently, it was very easy to find an image of a cat online. Then we want the model to predict what kind of animal is on this picture. We could train this model ourselves, but it would take a lot of time, and we need a lot of data to do so. So maybe we could just use a pre-trained model. Let's try and do that. For example, we can use Google Cloud Vision API. So what result do we get if we take this image of this cat, put it into Google Cloud Vision API? What is the result? And now I don't know if it is the file name which gave it away, but apparently Google can tell that this is actually a cat. And Google is pretty smart about this, so it can. It also gives us a lot of other labels. That this is a mammal, it has whiskers, and so on. What we just saw here was an example of classification. And classification takes an input or some features and maps it to a limited set of categories. For example, it maps to cat, dog, horse, and so on. We also have regression. And regression takes an input, some features, and maps it to a continuous value. So let's look at regression. For example, if we want to predict house prices in Oslo, this is an example of a regression problem, because a house price, that is a continuous value, ranging, for example, from 2 million Norwegian kroner to many Norwegian kroner. This model it needs some features. And a good feature is a feature that tells something about a house price. So, for example, here, the size of a house, it tells something about the price of a house. Also, the number of rooms. Well, if there are more rooms, there's probably the house becomes more expensive. And the same with the number of floors. So these three features, they are probably good features in this example. Hopefully, now the definition makes a bit more sense, and we can even rewrite it a bit. So it gets supervised learning is the machine learning task of learning a function that maps a set of features to an output based on labeled training data. Okay. We now more or less know how a model works, that we can take an input and then the model will give us a prediction, an output. But how do we come up with this model? We're going to take a look at that now. To make things a bit easier for us and to, in a couple of minutes, visualize the development of a model a bit better, I'm going to reduce the number of features to just one. So we just look at the house size and call this feature X. The next thing we need is some sample data. And we have that here. On the x-axis, we have the feature, the house size. And on the y-axis, we have the labels. We have the house price. Oh, did I say something wrong? On the x-axis, we have the house size in square meters. And on the y-axis, we have the house price. The next thing we need to come up with is this function that the definition talked about. A function that can map all of our sample data in a good way. And this is called a hypothesis. And let's just try and come up with a function. It looks like there's a somewhat linear trend in this data. So we come up with a linear function. And is this a function that maps our sample data in a good way? Well, maybe yes. Maybe it looks like we have a bit more data below the function, but it's okay. But what about this one? Is it better? Maybe. We need to somehow tell which of these ones are best. So what we're going to do, we are going to introduce some feature weights. We're going to introduce theta 0 and theta 1. And our goal now is to find values for these two thetas. And to do this, first we need some notation, where m is the number of training examples, and xi, yi is a specific training example. Next thing we're going to find is the cost of a single training example. And the next thing, we define the cost function. And again, I'm not going into details of why the cost function is like this. But a very important thing to know here is that the cost function, if we minimize the value of the cost function, we will get the optimal values of theta 0 and theta 1. So that's our next objective. It is to minimize this cost function. But before we do so, let's again take a look at this linear hypothesis with just a single feature. Because we will see later on that to make a Lego car drive by itself, we need more than just one feature. So let's expand it a bit to more features. So now we don't just have x, we have features x1, x2, x3, and so on. And for each feature, we also have a feature weight, theta. So now we also have xj, a specific feature, and theta j, a specific feature weight. Okay, again remember, our objective right now, it is to minimize the cost function. And to do this, we use an algorithm called gradient descent. And again, I'm not going into details why the algorithm is like this, but the main thing to take with you here is that we repeat something a number of times, and what we repeat is that in each iteration, we get a value for each feature weight, each theta. That is just a small bit better than in the last iteration. And we repeat this a number of times. And how many times are we going to repeat this? Well, that depends on the problem. And it depends on, here we have it, the feature weight, alpha. We are coming back to this, and we will see how many times do we need to repeat this and how to find a good value for alpha. Okay, that's enough with the math for now. So let's go back to Lego. Because our main objective, as I have said a couple of times, is to make a Lego car steer by itself. And to do so, we, of course, need a Lego car. So I made a fairly simple car here. It contains two motors, one motor for driving and one motor for steering the front wheels. In addition, it also has a sensor which can tell when the steering is in the most left or most right position. So now we have machine learning. We have Lego. What more do we need for a fun night? We need an app, of course. Everybody needs an app. So I created an app which can do three different things. It can collect data. It can train the model with gradient descent. And lastly, it can test drive the trained model. So the first thing, collect data. How do we collect data? Let's take a step back and more in general, how do one collect data for a machine learning problem? Well, if you have an Android phone, for example, then chances are that you are helping Google right now collecting data for their machine learning algorithms. You're probably doing that. And if we take a step back to when we looked at this Google Vision API, where Google can tell us what is on a picture. Actually, you can also help Google collect sample data for this. You can, for example, go to crowdsource.google.com. I did that. I registered, and now, if I go into this site, Google gives me questions. They gave me this question. Are there any buses in this picture? And I can select no or yes. And I, of course, selected yes, because there is actually a bus in this picture. And what I was thinking here is that, well, Google knows everything. Google, of course, knows that there is a bus in this picture. So is this a trick question or? But when I clicked yes, I got another question. Well, actually, I got the same question, but with another picture. Are there any buses in this picture? So apparently, Google doesn't really know if there is a bus in this picture. But they do now. I said no, there isn't. So there are many different ways of collecting data. For our problem, how are we going to collect data? Well, first we need to decide which data are we going to collect. We need to decide which features to use. So we have a Lego car. It is going to drive on top of a black line. The black line, is that a feature? Well, yes, it is. What about the rest of the road in front of the Lego car. Is that a feature? Oh, yes, most certainly, most certainly. So the road in front of the Lego car, that's a feature. And how are we going to see the road in front of the car? We are placing a smartphone in front of it with a camera. When I click collect the data in the app, we get to this page, where here we see the camera view, everything the camera sees in front of the Lego car. And can we then use all of this camera view as a feature? Well, we could probably do that. And now I say a feature, but here we actually have multiple features. We could say that each single pixel in this picture is a feature. And we could most certainly do that. But this gradient descent that we took a look at before, I have implemented that in a very simple way in the app, and I have not used any framework like a Google TensorFlow or something like that. So actually, that algorithm is not that fast. And the more features we have, it just takes longer to compute. So I'm guessing that using all pixels here will take too much time. And also, we want this to be as simple as possible. So instead, let's see if we can use just a single row of pixels and see if that's enough to get the Lego car to steer by itself. So we use this red line here. That's all the pixels in that line. That is our features. And the picture we have here below, that's actually the same. It's just that single pixel row stretched in the vertical direction. One last thing we need, because now we have defined our features, we also need to know what is our label, what is the output that we want to predict. We want to predict the steering, so let us just predict the steering angle of the front wheels of the Lego car. Now, we have defined our features, we have defined the label, but how are we actually going to collect this data? Could we just take the Lego car, put it on top of the black line, and then angle the steering a bit, take a picture, and manually say, well, I think it's 10 degrees, or I don't think that would work. So instead, we are going to collect data steering the Lego car manually with a controller. Let's see what it looks like. I click collect data and I give the model a name. Create the model. And every time we do something with this Lego car, it needs to initialize the steering. So it goes all the way to right, all the way to left, all the way to right, and centers the steering. Just, so we know that where the center position is. And now, just one note. The driving motor, I have disconnected that because otherwise, the car would just continue straight on. But you see here how the steering is actually working. When I steer the controller, the car is steering. Yeah. Next thing we need is a training course. And to much happiness of the rest of the house's residents, I removed all the furniture from the kitchen and decorated the floor with black tape. So now we have a training course. Let's collect some data. I again click collect data and I give the model a name. The steering is initialized and wait for a bit. And there we have it. I turn on the camera flash and I start collect data. And what we see here, we have seen it before. We have the camera view. We have this stretched pixel line, the pixels that we are actually collecting. And here we have a red vertical line. And that red vertical line, that is the steering angle that I am actually steering with the controller. And you see here that there's a bit of lag time. It takes a bit of, it doesn't update that fast, the bottom picture. But every time it updates, we collect sample data. So yeah, we collect, and we need to collect a lot of data. So round and round I go. Now we collect a lot of data, mainly going left. But we also want the car to be able to drive right. And we can't make it go right if we haven't got enough data going right. So I turn the car 180 degrees, and guess what happens? Yep, continue. And I collect more data. Yep, that was a fun afternoon. What do we actually collect? Well, we collect, this is what I actually collected. And here we have, on the left, the labels, the steering angle, ranging from, not actually an angle, but the angle in percent from 0 to 100. And on right here, we have all the features. We have the first feature, that is the pixel value of the first pixel value of the next pixel, and so on. So we have one row of pixels. Yep, done. So now we have data. The next thing we're going to do, we want to train the model. So let's take a step back. Remember this linear hypothesis. We can rewrite it just a bit, so it maybe makes a bit more sense that we have a function that says the steering angle is equal to theta 0 plus theta 1 multiplied with the first pixel value plus and so on. And again, remember these theta values, they are our feature weights. And when we are training the model, we are actually just finding the best values for these theta values. And remember how we do that? We do that with gradient descent, where we repeat a number of times an algorithm, and also we must find a good value for this learning rate. Okay, so let's do all that. Yes. The learning rate. I have cheated a bit. I tested some different learning rates, and I came up with a good one. A good learning rate was 1. So I set alpha equals to 1. And we will see now gradient descent working. And when is gradient descent working? Remember that in each iteration, we get slightly better values for theta. And when we get slightly better values for theta, we get a slightly lower cost. And again, remember that our objective right now is actually to minimize the cost. So what I have done on the right in the app is to plot the cost in each iteration. And we see here that in 500 iterations with a learning rate of 1, we see that gradient descent is working because the cost is getting lower in each iteration. We also see that the learning rate is a good learning rate because we see that the cost is converging. And when the cost is converging, it has been minimized. So now we actually have a trained model. We have found the best possible values of all these theta values. But again, I said that I cheated a bit. We just used a learning rate of 1. But what if we pick a smaller learning rate? What will that look like? Let's see. Now we pick a learning rate of 0.001. And again, let's take 500 iterations, the same as before. We will now see that gradient descent is working. The cost is getting lower. So, yep, it is working. But we also see that in 500 iterations, we do not see, see the cost converging. So again, it's working, but gradient descent is just working slowly. And that's why a learning rate of 1 in this case is better. But because we do not have a lot of training data right now. But imagine that I walked around in my kitchen for much longer period, then we would have more training data and gradient descent would be slower. So yep, we always want a good learning rate. Now, some of you are probably thinking, well, why don't we just pick an even bigger learning rate? It looks like that when we have a big learning rate, everything goes faster, and that's awesome. Not always. So let's now pick a bigger learning model. Let's learning rate. Again, 500 iterations and a learning rate of 2.5. Now we see that gradient descent is not working because in each iteration the cost is not becoming lower. In some iterations it is, but it needs to get lower in all iterations. So the cost is fluctuating and over time it is increasing. So this is not a good learning rate. We need a smaller learning rate. And just for the fun of it, let's try a very big learning rate. Let's use a learning rate of 100 and again 500 iterations. Now we get an error. And we get an error because in the first iteration, the cost gets so big that it cannot be contained in a 32-bit float. And yeah, the app simply generates an error. But now we have a model, a trained machine learning model. So let's do a test drive. And yes, it was my time to take care of the baby, so yeah. We initialize the steering again. Turn on the camera flash. And we start driving. And what we see here, before we had a red line, that was the line that I manually steered. The blue line here, that's the predicted steering angle from the model. Otherwise, the view of this driving page in the app is more or less the same. We still have the camera view in front of the car and this single pixel row, our features stretched. Well, that worked fine, didn't it? Perfect. But we now have 25 minutes left. Okay, but let's continue. Let's see. Let's speed it up a bit. Oh, damn it. No. Went off course. If this was a Tesla, we would have crashed. No, and again, no, doesn't work. Let's continue, let's see. Nope, angry baby, it doesn't work. Nope. Okay, what's going on here? We have a model which seems to work sometimes, but it's just not working well enough. So let's examine that. It turns out that we have two different error situations. Let's look at the first one first. We see here that the black line goes left, so we also steer left. But what we will also see is that when the camera just sees about half of the black line, then the model or the car doesn't know what to do. So you see here that it just continues straight on. And when it continues straight on, it doesn't see the black line and it doesn't know what to do. So that's a problem. And why is that? Well, we have just tried one model. We have tried this linear model. Is this the right model for this problem? Maybe, maybe not. Do we have some bad data? Do we have enough data of the car driving left? Maybe, maybe not. Do we have bad hardware? When I have been steering, can the camera actually see all of the road in front of it? Maybe, maybe not. The next error situation. Again, the car is going left, but then look at the black line. Suddenly, the black line is not that black anymore. It turns more of a grayish color. Let's see it again. Yep, here it turns gray. And when the black line turns gray, the model don't know what to do. And again, that's a problem. Same as before, do we have the right model? Maybe some bad data. Have we trained for this? Well, it actually turns out that the second problem, we can solve that in a very easy manner. We can use a well-known machine learning technique called the curtain fall procedure. And that's very easy to implement. So let's do that. There it was. Very easy to implement, very fast. And this may seem like a joke, but when working with sensors or cameras, sometimes it's just easier to fix things on the hardware side than it is to fix things on the software side. So for now, quick fix. What about the model? Do we have the right model for this? Let's take a step back and look at the data we had for house prices in Oslo. Here we chose this linear model. And the straight line we have here, the function we have here, is the best possible function for this sample data. Let's come up with another model. Here we have added the squared feature x. Does this model map the sample data in a better way? Well, usually when doing machine learning, you would have some test data that is different from your training data. And you would just test these two models and see which model is performing best on the test set. In principle, we could do the same, but of course, we're dealing with Lego, so we take a more practical approach. So in a bit, we will just test drive two different models and see which model drives better. And just to make everything clear, we have the function we used before. The steering angle is equal to something. And now we add squared features. Again, all the squared pixel values. We use the same training data, and I train with gradient descent. We're not going to show that again. Okay, ready for a new test drive, now with a new model. again, the same training data as before. When we have done gradient descent, we now initialize the steering. Turn the camera flash on, and we drive. If you're wondering why I turn the camera flash on, that's just to make the data a bit better, to make the light part of the picture a bit lighter without actually doing the black line lighter. Yeah. We saw that it's working. We have a better model now. But just for the sake of it, let's turn the car 180 degrees. And yeah, there's a reason why it doesn't go so fast right now. Yeah, again, mini Tesla crashed. And let's continue, and nope. It looks like we have a better model, but unfortunately, we still have problems. Yep, and the baby have learned to walk since last. Okay, so now we have a better model. But let's look at the hardware. The camera, I said before, maybe the camera doesn't see all of the road in front of it. So we can try and change the angle of the camera just a bit, so that we see this feature line that we use, the pixel line, it becomes a bit closer to the robot. And when it becomes a bit closer to the robot, we will see that the black line hopefully will not disappear out of the picture just as easy. So we try and change that as well. So what have we done so far? Well, we have fixed the light conditions. We have come up with a new model, and we have tested the new model, and it looks like it is better. We have changed the hardware just a bit. We don't know if it's better, but we have changed it. What about the data? Let's examine the data from we collected earlier. Yes, so we will now see again the data collection we did earlier. But in some parts I will slow down just a bit so we can see what we are actually collecting. Fast, 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 and here we see it. We see, again, every time the bottom picture updates, that is when we collect data. And we will see that sometimes we do not see the black line in the picture. And that's a problem, because what is it we want to do? We want to follow a black line. If we cannot see the black line, that's a problem. What is the model going to do? One thing we could do is manually to go through all the data that we have and remove all the bad data. Maybe that would give us a better model. I've not tested that, but I think you would get a better model. But this is also a problem because probably we do not have enough data going left and going right. Yeah. Okay. Now we have modified the car. And when we have modified the car, we need new data. We cannot use the same data anymore. So let's collect new data. And also, I will make sure that I'm a bit more concentrated so that I actually steer the car on top of the black line and not go too much left and right. So let's collect. And we collected in both directions. And if you counted the seconds, then yes, I did walk around in circles in my kitchen for 20 minutes. Okay, now we have a new model. We have data. And behind the scenes, I have done gradient descent, so we have trained the model. Let us test drive again. Again, we initialize the steering all the way left, all the way right, and then sensor position. Turn on the camera flash, and we start driving. Fingers crossed. Speed it up a bit. And we slow it down here. Here we had a problem earlier. It looks better now. And one thing that you can take a note at here is that the predicted steering angle sometimes get all the way to 0%, all the way to the left, and all the way to the right, 100%. We did not see that before. So it looks like the car can actually steer when it's sharp turns to both the left and to the right. But just to make sure, we turn the car 180 degrees and see if it's working, going mostly right. Again, here we had a problem before, also with the new model. So again, it looks better now. Yep, it looks like we now have a Lego car which can steer by itself. Woohoo! Perfect. But then, when I was testing all this, I had a visit from my neighbor, and he said, "What are you doing?" And I said, "Well, I'm working with Lego." And he replied, "Nope, you're playing with the Lego." I then explained what I was actually doing, and he said, "Well, that is quite cool, but this Lego car of yours, isn't it quite slow? Can we make it go any faster?" And I said, "Well, maybe. I don't think so, but we can test it. So let's speed it up a bit." And again, I know that it's not really fast, but it is quite a lot faster than before. And what we will see here is that it is working somewhat, but we will also see now that in sharp corners, that it becomes a bit too wiggly to the left and to the right, can't really follow the line, and now wiggly, and no. So no, it's not working. And why is that? Well, there are several reasons for this. First of all, there is a hardware problem. The steering on this car is simply not fast enough. So it can't change direction as fast as the line is changing. Another reason is that the model is trained at a lower speed. So the model is probably not working either. Also, the way that I have implemented this, it is implemented, and you can go and check for yourself later, implemented this in a very simple way, which also makes everything a bit slow. We could have implemented it in a better way so that, maybe it would work a bit faster and a bit better. Okay, let's see, what have we learned today? Well, know your data. Well, one thing I want to say is that many of the things we have gone through today, they seem very Lego specific, but actually many of the problems here and solutions, they can somehow actually be changed also when doing normal machine learning. So know your data. That's very important. And in that, also know when you have bad data. And also remove bad data. If we have bad data, for example, in our case, we have a pixel row without the black line on it, we cannot use that. We have also seen how to find the best learning rate by plotting the cost over each iteration when doing gradient descent. Another important thing is to measure model performance, and in that, pick the right model. And again, when doing normal machine learning, you would have a test set where you measured your performance, but in this case, we just did a more manual approach by finding out which model steered better. Also, we can just make the model make predictions within the limits of the training data. If we do not have enough data going sharp left, then the model doesn't know how to go left. Can we make any improvements? Again, this is just improvements to the problem of following a black line. We could most certainly collect more data. I am guessing that if I walked around in my kitchen not just for 20 minutes, but for several hours, then we would make the car work even better. Also, we could maybe collect data in different light conditions. Maybe we could even add a light sensor to the car and use the value from the light sensor as a feature. Maybe that would make the car steer better in different light conditions. Now we just used a single pixel row as features. Would the car steer better if we used all of the camera view? Well, maybe. Maybe it would. Again, if we were to do this, we would probably not use homemade implementation of gradient descent. You would probably use Google TensorFlow or something like that. Maybe you would even collect data on your on the car, on the smartphone, and then do gradient descent on a normal PC, for example. It would probably be a lot faster. We could test other models. Now we have tested 2 different models, but there are many different machine learning models. We could, for example, use a neural network or something else. And along with the first point, more data, if we could collect data faster, then we could collect more data in the same time. Okay, that was improvements to the problem that of following a black line. But in the real world, cars don't just follow black lines, unfortunately. That would make things a bit easier. So maybe we can come up with something that is maybe not Tesla, but something that is a bit more realistic. And what I will say now is not something that I have implemented. It is just if you, for some reason, want to do all of this at home, then after doing that, maybe can I improve on this? So this is just some input on that. Here we have 3 different roads, and maybe they are not real roads, but they are more realistic than just following a black line. Here we have, we have different road surfaces, different colors, and also we have different sides of the road. For example, maybe the side of the road is not the same if you are driving on a motorway compared to a smaller road. And we want the car to be able to stay on the road in all situations. How could we implement this? Well, maybe instead of instead of doing everything in one machine learning model, you could maybe do it in several steps. First step could maybe be to find where is the road. Wrong button. Here we have the road, and we have converted that here. So that all different roads, they are converted into something that will look the same for different roads. And from that, have a model that finds the steering angle. But this is up to you to try at home. Now, what's that? One more test drive? Yes. Because when working with machine learning, then we cannot test a model on the same data that we trained the model. And in our case, it's actually a bit wrong to to test the model on the same training course that where we collected the training data. So now I have made an even bigger course going all the way to the living room. And you will see here that it is actually working also on another course. If you want to do this at home, or just want to see what I have been playing with, then the source code for the app that does everything here, that's available. I will also say that right now it doesn't come with any explanation of any sort. It's just the pure source code. Later this summer, it will be updated with a bit more information, so it will be easier to find out what's actually going on. But have a look if you are interested. Also, time is running out, but if you have any questions, then I am outside for most of the day at the Itera stand. Thank you very much.